So one good way of thinking about integration is that it's a way of sort of adding up infinitely many quantities, really a continuum of quantities. And this idea is powerful for when we, especially if we look at things sort of geometrically. So for example, we just got done finding the area between two curves. And the way we did this is we represented, we integrated from the leftmost point to the rightmost point of the region, the height of vertical slices of this region. Now, in a sense, we're thinking of integral as sort of adding up all of these slices, because if we chop up this entire region into a bunch of vertical lines, one for every number x between a and b, and put them together geometrically, we get the area. And the integral is supposed to represent, in this mindset then, taking all of these lengths and adding them up to get an area. So this generally happens when we take an integral. Sort of the dimension goes up by 1. When we integrate velocity, we get displacement. So we get from, say, meters per second to meters. The dimension goes up 1 because we lose the seconds in the denominator. Over here, we start with the dimension being one-dimensional height, and we integrate over another measure of distance, I suppose length, and we end up getting area, which is height times length. So extending this idea, you might think that we can come up with a way to get volumes via integration, and you would be correct. The idea is going to be very similar. We're going to take a three-dimensional shape like this, and we're going to imagine that we're cutting it up into a bunch of flat parallel slices. And a really good way of doing this is to align an object, the object along an axis, and to slice it up into flat slices that are perpendicular to this axis between, and if the thing lies between A and B, then we get one slice for every value of x between A and B, and so there's an area of each of these slices. If we integrate this area from A to B, we end up with the volume. If we put all the slices together, we get the whole volume. If we integrate the area of the slices, we get the quantity that is the volume of this shape. As a very simple example, let's find the volume of a rectangular box with dimensions h, its height, w, its width, and l, its length, using integration. So here I've drawn a rectangular box, and its dimensions are height, h, width, w, and I need to align it along an axis. And really the easiest way for me to align this along an axis is for the axis to lie on one of the sides of the rectangle, because then every single slice perpendicular to this axis is just going to be a rectangle which is parallel to these bases of the rectangle here. And so I'm just choosing to put this axis along this long edge here between along the length dimension. And so it makes sense for me to let 0 be, say, where it starts, and then L is where the box ends, because that's how long it is. So when I do this, what I have to do is I have to figure out what the area of a typical cross section of the box is. Well, every single cross section of this box is exactly the same. It's the same as this base or this base. It's a rectangle of height h and width w, so its area is h times w. So the volume of the whole box is the integral from 0 to L of the height times the width dx. When I integrate that, h and w I'm treating as constants. So its integral, its antiderivative is hwx. I'm evaluating this from 0 to L, so I plug in L for x and 0 for x, and I subtract the lower limit from the upper. And the second term here is 0, so I'm just left with height times width times length. That's not really enlightening to see that the volume of a box is indeed given by height times width times length, but at least this illustrates how we can use this technique of integration to find volumes. Okay, so we're going to find the volume of a pyramid with height h and square base of side length s. So we can assume that the tip, vertex, whatever of the pyramid lies directly over the center of the square base S. Turns out that it doesn't matter for our volume computations, but whatever. Generally, I'll draw a picture for you so you have the right idea of what exact shape we're looking at. Anyways, I'm going to orient it sideways like this along the x-axis, because what that allows me to do is get all of my, if I put the vertex at 0, so that the x-axis goes through the bottom at x equal to h, then all of my cross sections perpendicular to the x-axis will be squares. So this is a square. So I just need to figure out what the side length of this guy is in order to figure out the area of the cross section at x. To do this, I use geometry. If I look at the pyramid sort of head on, stand it back on its square base and imagine that I'm staring at its face, its bottom has length s and it's a triangle of height h. Well, when I take the cross section at x, the piece of the pyramid lying to the left of x gives me a smaller pyramid which is similar to the whole big pyramid. That means it's has all the same angles and whatever, it's just sort of scaled down. In particular, if I look at that head on, it is a triangle that is similar to this one that I get from the whole pyramid. I know that its height is x because that's how I'm finding this cross section, and the length of its base is going to be the side length of the square that I'm looking for. So using the fact that similar triangles are proportional to each other, and since x is equal to, and since s is s times h divided by h, I can get this side length over here by multiplying x by s over h. So this is sx over h. Great. That means that the area of this square is this side length squared, sx over h squared. So the volume is going to be the integral from 0 to h. That's where my solid is located on the axis between 0 and h, of squaring this out, s squared x squared over h squared dx. Integrating s and h are constants. X is the variable. I use the power rule, increase it 2 to 3, divide by 3. I get s squared x cubed over 3h squared from 0 to h. Plugging in, I get s squared h cubed over 3h squared minus s squared 0 cubed over 3h squared. And that simplifies to s squared h over 3, which is the formula for the volume of a pyramid. All right, so now let's find the volume of the following triangular wedge. So what this is it's pretty much a pyramid. It's a shape which comes to a point over here and has a right triangular base over here. And the dimensions of it are from this point to this base, so a distance of 3. This length right here is 1, this length right here is 2, so this is a right triangle with lengths 1 and 2 right here. And just to give you some more to work with, this triangular base is perpendicular to the x-axis, so that means that all cuts perpendicular to the x-axis here are going to be right triangles that are similar to this right triangle. So if you know the area of this, you should be able to find the area of this guy using some geometry and similar triangles and stuff like that. All right, go ahead.